Good afternoon everybody. Myself Manjeet Singh, working as a senior lecturer at Government Polytechnic College Bathinda. Today I am going to deliver a lecture on optical amplifiers. The subject is Optical Fiber Communication, 6th semester EC. Now let us first discuss about the optical amplifiers. An optical amplifier is a device that amplifies an optical signal directly without the need to first convert into an electrical signal. In conventional system, first we convert the optical signal into electrical signals, then we amplify the signal in electrical form, then at the receiving end again convert electrical to optical. But in this case, in case of optical amplifiers, the signal this device amplifies directly the optical signal without converting it into electrical signal. An optical amplifier may be thought of as a laser without an optical cavity or one in which the feedback from the cavity is suppressed. Optical amplifiers are important in optical fiber communication and laser physics, because in both these cases we have to amplify the optical signal. So, optical amplifiers are used in optical fiber communication and in laser physics to amplify the optical signals. Now, the optical fiber amplifier was invented by H.J. Shah and Michael Dagnonet at Standard University of California in 1980s. So, a sample of optical fiber amplifier is shown, optical amplifier is shown, means it is a device that amplifies optical signal directly without the need to first convert into an electrical signal. An optical amplifier may be thought of as a amplifier without the optical cavity or one in which the feedback from the cavity is suppressed. So, this is the same thing which was introduced in first slide. There are several different physical mechanisms that can be used to amplify a light signal, which correspond to a major types of optical amplifiers. Stimulated emission in the amplifier's gain medium causes amplification of incoming the light. So, there are several methods or means which are used in these optical amplifiers, but stimulated emission is one of the major medium that I use to amplify the signals. Now, next is why we use amplifier, why amplifier are used. So, we know that in order to transmit a signal over long distances, it is necessary to compensate for attenuation losses, because attenuation occurs as the signal travels. So, to compensate that attenuation losses, we use the amplifiers. So, this is the basic diagram of simple amplifiers. In this case, first optical fiber means optical signal in a optical fiber, then optoelectrical devices means optical to electrical conversion, then electronic amplifier, equalization and regeneration circuits. So, again at the receiving side, then electrical to optical transducer is used, then again the fiber and the optical signal out. This is a conventional system. In this case, the signal is first converted from optical to electrical, then its amplified or equalization or regeneration is done, then again it is converted into optical signals. So, initially this was done with an optoelectronic module. So, these devices which converts optical to electrical or electrical to optical are called optoelectronic devices or optoelectronic modules, consisting of an optical receiver, then regeneration and equalization systems and the optical transmitter to send the data. Although this functional arrangement is limited by the optical to electrical and electrical to optical conversions. So, this is a conventional system. In this, the conversions are done from optical to electrical and then from electrical to optical by using optoelectronic devices as transducers. Now, why we use optical amplifier? So, this is the diagram of optical amplifier. So, in this case the optical input signal is shown as rectangular waves. Then fiber to amplifier couplers, the couplers are used at both at the starting or at the end of this active medium. Active medium is basically optical amplifier. So, it is supplemented by a pump source. So, pump source and active medium amplifiers, this is basically the concept of optical amplifier. So, it amplifies the signals in optically, then at the receiving side again a coupler is used, and the output is a amplified optical signal which is shown. So, this is the concept of optical amplifier. Several types of optical amplifiers have since been demonstrated to replace the optoelectric electronic regeneration system, that is traditional system. These systems eliminate the need of optoelectric and electric to optical conversions. This is one of the main reasons for the success of today's optical communication system, because in this today's optical communication system, optical amplifiers are used, means optical signals are amplified directly without converting them into electrical signals. So, again optical amplifiers, the general form of optical amplifier is as shown in figure. Optical signal in means this is a optical fiber, beak signal means naturally the signal which we are going to amplify is a beak signal. Then optical amplifier medium, that is basically a basic optical amplifier. So, this amplifier or this medium amplifies the optical signals. Then at the end of this medium the amplified signals. So, beak signal is converted into amplified signal, means the signal is amplified. Then it goes through the fiber and the optical signal out at the other end. Now, this was about the optical amplifiers. Now, what are the different types of optical amplifiers? So, some types of optical amplifiers that have been demonstrated in the coming slides include, first one is, that is most important and most commonly used, is semiconductor optical amplifiers, commonly called SOA. Then next one is doped fiber amplifiers. Then third one is fiber Raman and Brillouin amplifiers, and the fourth one is rare earth doped fiber amplifier. This is a type of doped amplifiers. So, these are the some commonly used types of optical amplifiers. We will discuss these types one by one. Now, first semiconductor optical amplifier SOA. Semiconductor optical amplifiers SOAs are amplifiers which use a semiconductor to provide the gain medium. So, as it is clear from the name that semiconductors are used to provide the gain. These amplifiers have a similar structure to Fabry Perot laser diodes, but with anti-reflection design elements at the end faces, means in this case the reflection elements are used. These designs includes anti-reflective coatings and tilted wave guides and window regions which can reduce end face reflections to less than 0.001%. This is the main advantage of these types of amplifiers. Since this creates a losses of power from the cavity which is greater than the gain, it prevents the amplifier from acting as a laser. Semiconductor optical amplifiers are typically made from group 3 to 5 compound semiconductors such as gallium arsenide, aluminum gallium arsenide, indium phosphide, indium gallium arsenides, indium phosphides, indium gallium arsenide phosphides, and indium phosphide, indium aluminum gallium arsenides. These are few names from these groups. Though any direct band gap semiconductors such as group 2nd to 6th could also be used in this semiconductor optical amplifiers. Now, this is the sample of optical amplifiers. Such amplifiers are often used in telecommunication systems, in optical fiber communication system, in the form of fiber pigtail components. So, this components is shown operating at signal wavelengths between 0.05 micrometer and 1.6 micrometer and generating the gains of up to 30 dB. Now, the semiconductor optical amplifier is of small size and electrically pumped. It can be potentially less expensive than the EDFA. EDFA is another type of amplifier which we will discuss, and can be integrated with semiconductor laser modulators, etc. So, this is a saturable semiconductor optical amplifier. So, in this input signal which is a beak signal, then the optical medium, the optical amplifier. So, the output is a high amplitude amplified optical signals. So, quantum dots and electric current directions are shown. So, this is the concept of saturable semiconductor optical amplifier. However, the performance is still not comparable with the EDFA. The semiconductor optical amplifier has higher noise, lower gain, moderate polarization, dependence and high nonlinearity with fast transit time. These are the few advantages and disadvantages or some parameters of this semiconductor optical amplifiers. The advantage of semiconductor optical amplifier is that all four types of nonlinear operations like cross gain modulation, cross phase modulation, wavelength conversions and 4-wave mixing can be conducted. Furthermore, semiconductor optical amplifier can be run with a low power laser. This is the plus point of this amplifier. This originates from the short nanosecond or less upper state lifetime, so that the gain reacts rapidly to change of pump or signal power, and the changes of gain also causes phase changes which can distort the signals. So, now this type of amplifier is shown. Weak optical signal is inputted, then semiconductor cavity which is the main mechanism, then anti-reflecting elements at the both ends, electric drive current direction is shown, the output is amplified optical signals. So, this is semiconductor optical amplifier. The main medium is a semiconductor cavity with anti-reflecting plates at the ends. This nonlinearity presents the most severe problems for optical communication applications. However, it provides the possibility for gain in different wavelength regions from the EDFA. Linear optical amplifiers using gain clamping techniques have been developed. High optical nonlinearity makes semiconductor amplifiers attractive for all optical signal processing like all optical switching and wavelength conversions. These are few applications where they are preferred. There has been much research on semiconductor optical amplifiers as elements for optical signal processing, wavelength conversions, clock recovery, signal demultiplexing and pattern recognition. Now, types of semiconductor optical amplifier. There are various kinds of or various types of semiconductor optical amplifiers, and the major types are: first one is Fabry Perot amplifier, commonly called FPA, and next is Traveling Wave Amplifier, that is TWA. We will discuss these types one by one in details. Fabry Perot amplifier. When the light enters FPA means Fabry Perot amplifier, it gets amplified as it reflects back and forth between the mirrors anti-emitted at the higher intensity. So, the reflection is the main concept. So, it is sensitive to temperature and input optical frequency. So, this is Fabry Perot amplifier. So, in this case the two mirrors are used, one at the front side and another at the end side. So, front side is mirror with reflectivity R2, mirror with reflectivity R1, means R1 and R2 are two different, means these mirrors are having different reflectivities. Then medium, active mediums, electric current and hole current directions are shown. So, in this case the optical signals enters and it comes out through the cavity. It is a type of semiconductor optical amplifier, and as shown in the figure that how the light enters the active region is the main cavity, is reflected several times from the cleaved face and leaves the cavity after amplification. The output of the cavity is amplified signals. Two mirrors, the two mirrors used at the start and at the end side have active medium between them, that is the main semiconductor medium, forms a laser type concept. Mirrors are required to provide positive feedback. These mirrors provides positive feedback through reflections. This arrangement helps the return to stimulated photons. So, stimulation is the main concept to the active region to stimulate more photons, means more photons are stimulated. The two mirrors form the resonator, L type resonators are formed using these two mirrors. Let the arbitrary wave travel from the left hand mirror to the right hand one. The wave have breaks in the phase, which is impossible here. So, this resonator does not support his phase. So, at right hand mirror, this wave undergoes a phase shift of 180 degree and continues to propagate. At the left hand mirror, this wave again has the same phase shift and continues to travel. So, this waveform yield a stable pattern called a standing wave. Now, next is traveling wave amplifier. So, it is the same as FPA, means Fabry Perot amplifier, except that the end facets are the anti-reflection coated or cleaved at an angle, so that the internal reflection does not take place and the input signal get amplified only once during a single pass through the device. This is the major difference between FPA and traveling wave amplifiers. So, they are widely used because they have a large optical bandwidth. Their optical bandwidth is large as compared to the FPA and low polarization sensitivity. Polarization sensitivity is also less as compared to FPA. So, this is the concept of optical traveling wave amplifier. So, in this case mirrors are used, then partial mirror, main mirror, then anti-reflecting coating are used. So, input signal is shown as a low signal, the output signal. So, in this case the signal that is called traveling wave amplifiers, means the signal amplifies continuously from starting to end. So, it is shown in red color at the down. The signal amplifies gradually as it travels from the starting to end side. So, input fiber, then lens are used, then active layer, then output fiber. So, signal is amplified gradually from input to output side, that is why it is called traveling wave amplifier. The signal amplifies as the wave travels from the input to output side. A traveling wave amplifier is essentially an active region without reflective faces, so that the input signal is amplified by a single pass through the active region. So, in this case the signal is amplified by a single pass, means the signal passes in a single pass from input side to output side through the active region, and the signal is amplified gradually from input to output. In traveling wave amplifier, semiconductor material have built-in phases, these have built-in phases, and these phases without any cleaving reflects back the active region. So, this is the unique characteristics. For traveling wave amplifier is required to have the reflectories much smaller than they are for an FPA. Hence, the product of gain and bandwidth of a traveling wave amplifier is larger than for an FPA. So, that is why this traveling wave amplifier is better than FPA, because the product of gain and bandwidth of this traveling wave amplifier is larger more than FPA, means Fabry Perot amplifier. That is why this is better and more commonly used. For single pass, gain is about 30 dB and bandwidth near 40 nanometer is commercially available in this traveling wave amplifiers. Now, these were the two types of semiconductor optical amplifiers. So, now what are the main applications of these semiconductor optical amplifiers? So, the applications are, they are used inline amplifiers. So, this is the major applications. Then they are used as a detectors, then they are used as a pre-amplifiers in optical fiber communication system. These are applications related to optical fiber communication systems. So, then in the system they are used as optical switching elements, they are used as wavelength converters, they are used as power boosters immediately after the laser diodes. So, these are the few major applications of semiconductor optical amplifiers in the optical fiber communication system. Now, what are the major characteristics of semiconductor optical amplifier? So, its major characteristics are they are polarization dependent. Secondly, they require polarization maintaining fiber. Third is their gain is relatively high, that is approximately 20 dB. Then output saturation power is 5 to 10 dB. Then larger bandwidth is larger. Next, they can operate at 800 nanometer, 1300 nanometer and 1500 nanometer wavelength region. So, these are the regions of major application. Next, they are compact and easily integrated with other devices. They can be easily integrated with other devices as they are compact in size. They can be integrated into arrays. This is the major characteristics, means we can use these amplifiers as into arrays, can be easily integrated into arrays. Then high noise figure and crosstalk levels due to nonlinear phenomena. So, these are few characteristics of semiconductor optical amplifiers. Now, next type is doped fiber amplifier, DFA. Doped fiber amplifiers are optical amplifiers that use a doped optical fiber as a gain medium to amplify an optical signals. So, this is a major major part, means these amplifiers are optical amplifiers that use a doped amplifier fiber, means here the optical fiber is doped as a gain medium to amplify the output signal. So, here the fiber actually the fiber is a unique fiber which is doped and used for amplification. They are related to fiber lasers. The signal to be amplified and a pump lasers are multiplexed into doped fiber and the signal is amplified through interaction with the doping ions. So, these are the major concepts of this amplifiers, these types of amplifiers. The most common example of this doped fiber amplifier is the Erbium-Doped Fiber Amplifier, that is EDFA. This type of amplifier is commonly used, where the core of silica fiber, in this case the core is silica, core of silica fiber is doped with trivalent erbium ions and can be efficiently pumped with a laser at the wavelength of 980 nanometer or 1480 nanometer and exhibits gain in the 1550 nanometer regions. So, the doped fiber amplifier is shown in this figure. In this case, the input signals are shown at the input. The signals are amplified, means they have higher amplitude at the output side. So, in this case, the fiber is a doped fiber as discussed in the previous slides. So, doped fiber is used, then a pump source is used. So, this is a conceptual diagram of doped fiber amplifiers. Here amplification is achieved by stimulation emission of photons from dopant ions in the doped fiber. This is the working principle. The pump laser excites ions into a higher energy, from where they can decay via stimulation emission of a photon at the signal wavelength back to the lower energy level. The excited ions can also decay spontaneously, means spontaneous emission, or even through non-radiative processes involving interactions with photons of glass matrix. These last two decay mechanism complete this stimulated emission, reducing the efficiency of light amplification. Here the amplification window of an optical amplifier is the range of optical wavelengths for which the amplifier yields a usable gain. The amplification window is determined by the spectroscopic properties of the dopant ions, the glass structures of the optical fiber and the wavelength and power of the pump laser. This is the mechanism. So, again in this types rare earth doped fiber amplifier. So, what is this rare earth doped fiber amplifier? Rare earth doped fiber amplifiers are finding increasing importance in optical communication systems. Perhaps the most important version is Erbium-Doped Fiber Amplifier. This is a rare earth doped fiber amplifier due to their availability to amplify signal at the low loss, that is 1.55 m wavelength range. So, the Erbium-Doped Fiber Amplifier is the most developed fiber amplifier as its amplification window coincides with the third transmission window of silica based optical fiber. So, here the two bands have developed in the third transmission window, that is the conventional or C band, means compromise band, from approximately 1525 nanometer to 1565 nanometer, and the long L band from approximately 1570 nanometer to 1610 nanometer. So, practical diagram of this Erbium-Doped fiber amplifier EDFA is shown. So, first its sample diagram is shown, then it is shown in the circuit EDFA. So, EDFA have two commonly used pumping bands, these are 980 nanometer and 1480 nanometer. The 980 nanometer band has a higher absorption cross section and is generally used where low noise performance is required. The absorption band is relatively narrow and so wavelength stabilized laser sources are typically needed in this type. The 1480 nanometer band has a lower but broader absorption cross section and is generally used for higher power amplifiers. A combination of both 980 nanometer and 1480 nanometer pumping is generally utilized in these type of amplifiers. So, again this amplifier is shown, input signal is a very big signal as shown, the output signal is higher amplitude signal, means the signal is amplified, then pump laser, pump source and coupler, that main coupling is used at the starting end, then Erbium-doped fiber means special type of fiber which is doped with the Erbium, that is the main amplification part, then filter at the filter is used at the output side. So, this is a conceptual diagram of this Erbium-doped fiber amplifier. So, here fiber is doped with the Erbium and this type of amplifier is constructed. So, here pumping is primarily done optically with the primary pump wavelengths at 1.48 m and 0.98 m as indicated. Atoms pumped to the 11/2, that is 0.98 m band decays to the primary emission radiation band. So, pumping with 1.48 m light is directly to the upper transition leaves of the emission band. So, here semiconductor lasers have been developed for both pump wavelengths. So, general EDFA amplifier configuration. General EDFA amplifier configuration is shown below. So, first coupler, first pump laser, that is 980 nanometer or 1480 nanometer pump laser is used. Then isolators naturally used at the starting end, weak input signals, then coupling device used, then a length of Erbium-doped fiber amplifier, means a length of optical fiber, then again isolator is used at the end, then narrow band filter is used and the output signal is amplified as comparison to the input signal. So, 10 to 20 milliwatt of absorbed pump power at these wavelengths can produce 30 to 40 dB of amplifier gain. So, here pump efficiencies of 11 dB milliwatt achieved at 980 nanometers. Pumping can also be performed at 820 and 670 nanometer with gallium aluminum arsenide laser diodes. Pump efficiencies are higher, but these lasers can be made with higher output power. So, gain spectrum of EDFA. Since the gain spectrum of erbium resembles a 3-level atoms, it is possible to model the gain property using this approach. Several different wavelength bands have been designed for wavelength division multiplexing, that is WDM, and EDFAs have been designed to operate in these bands. Now, what are the advantages of EDFA? The major advantages includes high power transfer efficiency.